Momentum. Everything is working. Yes. Working, but the USB varies. It won't work. Right. All right. So I am part of the beginner gravitational physics group here. So I'm technically working on large width gravitational waves and their simulations. Generally, I'm working with extreme binaries. So whether the mass is on a high scale or the mass ratio, the mass gap between the two components of the binary is big. But recently we decided to test code against codes that are used in the bigger libraries like LOL, and especially we are specializing in eccentric binaries. So we try to find the eccentric source code, which is the so-called CellBNR code, which is an acronym for spinning effective one-body numerical relativity eccentric code. So technically, this is a kind of branch from the one which is used in actual searches. So technically, searching goes like that. There is large template bank of gravitational waves. They are match filtering it on the data coming from the detectors, and then there are algorithms which way they can more accurately say what is the actual masses inside and the other parameters of the binary later on. For example, here is the gravitational wave data of the first detection of gravitational waves. Later on, it was fitted with such algorithms like CellBNR. So these codes mostly depending on numerical relativity, on the effective one-body, and sometimes Taylor expanded gravitational wave theory. It has its problems. So currently, most libraries working only on short gravitational waves. So the longest that is currently can be simulated is a few seconds. So we currently can't really the codes that is used at least I currently cannot simulate more than a few seconds of the gravitational radiation, which is how to say in alignment with the current capability of our detectors. So currently we are only capable of capturing just a few seconds of these waves, which is will change in the future drastically. So we are in a special need of codes that can actually simulate much longer period of times than these few seconds that is currently mostly used in the data bands. So as I mentioned, technically now coming the new detectors to the scene, namely detectors like the LISA, the LISA, which will be a space laser detector in space, which will have at least initially the idea was to have 5 million kilometer long arms. Now it's reduced to around 1 million kilometers, so it's still much larger what can be done on Earth. The other is are underground detectors, which will be built in Europe. The site not yet decided, which will be the Einstein telescope. Then the Americans will build the Cosmic Explorer, which is the same as the current detectors, just much larger. They have space for that. The Wide West. With these detectors, we will be able to detect much longer waves for two reasons. In small part because they will have larger arm ranges. Also, they will be measuring much longer times. So the current detectors not running 24/7 a week. So these detectors will be constantly on, and they will measure much new effects that we cannot see so far in the gravitational waves we detected. So, for example, they are predicting that we will be able to detect magnitudes more neutron star binaries, which will give us deeper insight how, for example, heavier elements created in the universe. So at this year, I can tell the good news that LISA get the green light from the European agencies, so they started to launch the satellites. And probably in a few years, it can start with observational runs. Just a little talk about gravitational waves and how they are coming from the general relativity. So technically, as early as Einstein brightened up his famous equation, it was seen that it has some kind of wave-like nature in it. So very early we finding evidences of gravitational wave in theory, but actually Einstein, his equation not really derived from the differential geometric geometric techniques. He technically derived it from the Hilbert-Einstein action. In the his formalisms, there was already can be seen some wave-like nature, but if we just use the differential geometric methods, we also can, by using the embedded gauge symmetries in the general relativity, see that we can break up the metric, which is telling us how to measure the distance in our space-time into two parts, to a flat metric and the perturbation on it. And technically, in this perturbation metric, we can go nuts. So technically, now it says more than 10 extension to this perturbation, which contains several. It's for so technically, if you know quantum units, there you can see some resemblance with the wave equations you can see frequently. And using some other stage conditions, we get this very simple equation, wave equation. Yeah, so now we have a wave equation, we detected gravitational waves, and we can break equations into parts. So there is a part of the gravitational wave which will represent the so-called inspiral phase. This is when our sources still are far from each other, so it's still just they are inspiraling. No? Spiraling too much. And then there is the so-called stable orbits after the gravitational force will become strong between the two. And there is the merger phase, and then the two black holes merging into the one. For black holes, it's simple. For neutron stars, it's become quite, how to say, not simple, because there you have to take the matter part into it, because inside neutron star there are no vacuum, while in black holes there is only the vacuum inside, so you can only have to count for the singularities, and that's where our physical knowledge breaks down. So actually we can just take them as points. And then the ring down phase, which is a very small part of it, and mostly the most easiest part. So technically our motivation mostly lies in the inspiral phase, and to see how different effects, for example, if the components inside the binary has spins, eccentricity, etc., and if we just adding effects like spin orbit effects, spin effects, spin coupling, spin self-coupling, how it will change the gravitational radiation. Also quite interesting effect that's also has effect on the orbital evolution of the system. For example, we are thinking about like spin flip-flop, and there is the spin flip, and the spin is changing the evolution. It can already show direct effect on the gravitational radiation. Also, if we are thinking about like if they are still different in the inspiral phase, there is the chance in long gravitational waves that is more than a month long. There's the spin changing its direction multiple times during the evolution, which will leave remarkable effects on the gravitational radiation. Also, it can, for example, if we by in eccentric binaries, we can find very interesting effects when, for example, from a very high eccentric orbit, the secondary component is captured, taking a few orbits around the primary black one, and then again starting a high eccentric orbit, which also will leave interesting effects on the gravitational radiation. Also, there is a which is a private research of mine. This is the orbital evolution of supermassive black hole binary, which is also, how to say with current detector techniques is a not observable one on Earth. We have to use other methods like pulsar timing arrays, where we are from the change in the parameters, we can see whether coming through gravitational wave, if there was a coming through gravitational wave. So generally, the problem is how we solve the two-body problem in these binaries, because from GR, directly from the Einstein equation is quite hard not to break. So technically, there are several methods developed during the years. So technically, the earliest is the numerical relativity, where they are breaking up the Einstein equation into solvable ones. But technically, here is the problem: is like when you are doing how to say a movie with a single photographing machine, and you're taking just pictures by pictures by pictures. So it's very accurate, very effective. We can simulate in any phase of the gravitational wave the dynamical evolution of the system. That is quite slow, quite resource extensive. Then there are other methods which is not good, for example, for the merger phase because they are not accurate enough. For example, the cell force and the post-Newtonian and the effective one body, but they are good in the other two phases of the gravitational waveform, the binary for the binary evolution. But we have to apply restrictions. So, for example, the post-Newtonian is usually called the slow motion weak field approach to the two-body problem. So we are restricting ourselves that the system cannot go fast. It means that the higher limit for the speed of the system is around the half of the speed of the light, and also the gravitational field cannot go beyond the current limit. While in the effective one body, we technically taking us, if we are restricting ourselves to the gravitational field of for a particle moving in the gravitational field for example, a rotating black hole. So we have one black hole and one particle with the mass of a black hole. This way we can simplify our equation. Cell force is a perturbational theory. It's technically we just implying some small effects, so it's mostly used for the ring down phase simulations. So a little bit about the two formalism. I meant to read the extensions. Currently, we reached the fourth post-Newtonian term at the moment. So as I said, we restricting our hands very direly in this situation. So technically, it's mostly only usable for the in spiral phase, where they are still apart from each other. So the field is still weak and the motion is still slow. But technically, with each new term, we are getting closer to the Einstein equation. So in hope we are converging towards the Einstein equation. So at some moments we will be able to reach much closer regions in the development of the binary. As I said, this is kind of this perturbational equation most of the time referred to as field equation. So here we the applied terms. It's mostly the main sequence terms and some spin orbit terms for the equation. So the other code use the so-called effective one-body. So as I said, it's technically a reduced Kerr metric. We use Kerr metric, and in this reduced Kerr metric, moving a test particle, a very massive one, which which is its motion is developed by this effective Hamiltonian, which containing the non-spinning part, spinning and the spin self-interacting part. So technically the test particle is interacting with its own spin. And it's a little bit for boot code. So we are use the spherical harmonic extension of the radiation field research. And to say for the eccentric part, they use the same equations. That's the post-Newton formalism using. So, as I mentioned, we use two codes, the Civiviz and SOBNR, which is basing on two different formalisms, but they're using the same integrator and somewhat using the same initial parameters space of them. So for initial parameter, which we are differentiated, we use the masses of the two components of the binary. So we taken 100 points between 10 and 100 in both component. We restricted that set, so we wanted to have short gravitational waveforms. So we started our simulation quite close to each other, and we restricted ourselves to the last stable orbit of the binary. So this is the technical limit for boot formalism. So BNR using some numerical relativistic techniques to also simulate the merger phase. So it's giving a complete gravitational radiation. So we have to cut these paths from the radiation for our research. This implies for the use 6 spin amplitude for our research. So for each amplitude, we have to do 10,000 simulations with each code, which give us a grand total of 260,000 simulations. And neither code was technically parallelized, so we cannot run a simulation where the simulation running through on each point on our configuration space. So we had to use high throughput techniques to computational techniques to finish this task in a short time before I am running out of my PhD time. So to this purpose, I configure the HT Condor cluster on our infrastructure. Technically, I used the our phi nodes as a execute node to connect the 4 phi nodes. I used the storage computer as the least used node by other users as a management node, as a central management, and the subnet node is currently the Opteron R gate computer. So to speak a little bit about how it was done. Technically, we could do the simple thing that I simply just installed the HD Condor. There is the documentation. It's not a very hard thing to do, but then there is the problem that you have the same slots throughout. So I would have 1,000 slots, but each slot would be have one CPU with the uniform memory and this space. So we decided to use dynamic slot management in our HT Condor cluster. So there is the CSCAMS that is currently available, the latest Condor. There is the so-called statistical, which is the old way where you have the uniform slots. It's good for counting jobs when you are sure that each job will take the same amount of resources. There is a partitionable ones. It's a step forward from the static one. And then there is the dynamic one, which is a little bit an extended version of the partitionable one, because in partitionable ones, you still have a restricted memory size, for example, and CPU size. Only you can partition the disk, change the disk size. In the dynamical size, everything is managed to the submission file. So there is for each execute node, we have one partitionable slot, as you can see on the upper figure. And there are dynamic slots created from it. So for example, if I don't need the entire cluster, I just need more memory and more disk space. For example, during when I done my data analysis, there I needed much bigger memory size because my file was bigger. So then I restricted the size. I choose bigger memory size, so I have fewer nodes. Instead of having 1,000 node slot, I have only 100 node, and then it was good for me because still much faster. It was still much faster than if I just run it in a single uniform memory slots, but would have taken much longer time to run to each slot because of the memory restriction. Yes, and to say it's not that hard to actually configure. Just you have to give these few lines to the HT Condor config file. And technically, we had 272 virtual CPU per execute node. I left 22 for the system to not overflow it with jobs. And then very simply, also submission can be done through the Python code. So technically, this is the a snippet that I used technically to generate the jobs during our runs. So technically, there is currently a Condor library that can be imported into the your Python code. And in this very simple code, you can technically submit jobs for your discretion. And technically, that's how I made tens of thousands of jobs. Also, with this, I could test the limits of HT Condor, at least on this cluster size, because initially we had more ambitious plans to have much more points between 10 and 100 solar mass. So there was a point I tried to send more than 500 jobs on the cluster, and that was the point where I reached the limit of the cluster, and then some point the jobs was cut by the HT Condor manager. So now then we can simulate now. So initially still we have to find the where we can match the most efficiently our two codes. So because there is two different formats, we have to find where our equations will give us the most similar results. So technically we started to find which is the time window where the evolution of the system is the most similar. It can we choose to analyze the evolution of the separation of the binary, so the distance between the two components, and we find there is a relatively small window marked with the green area in the plot where they are moving close. Also, we checked if we are changing the mass ratio, whether how it is changing. All right, I'm running out of time. So technically, we find that there are configurations. There are actual initial parameters where the root code on some restrictions on the post-Newtonian terms performing the same, almost the same. But we see how they are moving from each other if we are growing the mass ratio between the two masses. With this, we have the windows where we will measure how similar the gravitational waves generated by the two codes. For this, we use the mismatch or unfaithfulness of the two gravitational waveforms, which is a familiar thing for those who are working in signal processing. Please, technically, the weighted convolution of the two gravitational waveform, and the mismatch is actually this overlaps marginalization, and we use the so-called QBit Python library, which is developed for such to evaluate gravitational simulated gravitational wave by other codes. So by this, we could create these kinds of maps. We see that as the mass ratio between our two components is growing, the mismatch is getting worse and worse. But we also see some singular it is on our map. So we technically waited that there will be a continuous transition in our points, that we find some interesting effects on our maps. So technically, our initial guess was this may be a phases. There is no match in the phase, which is partly good, and mostly how good is our mismatch or overlap between the two codes is kind of given how this how the phases matches between the two codes and how much they are moving away from each other. So we done the similar for the spins in two different scanners when the spins are aligned or unaligned, which is aligned spins means the spins throughout the full evolution became perpendicular to the orbital phase. So in this case, there shouldn't be a spin precession during, so the orbitals also staying the same plane. So we seeing that there is a new region where the mismatch is getting worse. We done the same things for non-aligned spins for CB waves. We actually waited that the mismatch will get much worse between. To our surprise, we just see that more lines getting on our maps. So technically, because we doesn't see much difference between the aligned and the non-aligned spins, we get the suspicions that the spin doesn't remain aligned in CB waves, which in this over-orbital evaluation is proven. But still, for some reason, on the initially aligned spin configurations in CB waves, still we cannot see the effect of the spin pins like in the non-aligned chases. I need heavy waveforms. So I'm running to it, and just some thanking for the GPU laboratory for the resources. This work was made in collaboration with Barto Daniel, and advice this was given by Lars Varpadger. So thank you for your attention and some short questions. I survived.
Thank you very much. Is there any short question? Yes.
So in total, usually it was around 4 to 5 hours for the simulations, but technically it's was very varying. So technically, when the total masses and the mass ratios were small, it just was a few seconds. When was the total masses or the mass ratios big, then the distance also grown much larger. Even if we started closer, then it could reach hours. For example, there was actually some configuration where actually CBA is for some reason blown up. So technically, it has an iterative algorithm. You need to make it much more accurate and to iterate the parameter to some acceptable accuracy. It's 2 days for it to reach its point. So sometimes I have to play a little bit with the integration with the time step to be able to run the code in a affordable time frame.
Our speaker.
And thank you for all of the speakers of today, of course. There are still some snacks and drinks back, and yeah, so this is the end of today's last session, and thank you for your patience and your energy and your attention. So you can still stay here to discuss with each other, but otherwise, let's meet tomorrow at 9 a.m. So sharp, yes. Thank you.